Hi, this is a short video I'm recording for Project 5 in CSC 230. I was just going to try to go over how our compression technique is supposed to work. I've had a couple of students come up and they just wanted to talk about the general ideas of what we're doing. And I showed them some examples like this, or we talked through them, and that helped them feel better about the project. I'm really going through some of the same stuff that's in the project write-up, but maybe with a chance to talk through it, it will make a little bit more sense if you're having trouble understanding it. So we're implementing a LZW compressor. This is one that was developed, or this is a technique that was developed in the 80s. And it works by building a dictionary of words that show up in the input file. The idea is, as we build the dictionary, we can look for and when I say words, I mean sequences of bytes. So they might be strings or substrings that show up in the input, or if we're compressing a binary file, they might not really be strings at all. They could just be arbitrary sequences of bytes that happen to occur in the input file. So as we're reading the uncompressed file, whenever we see a sequence that we maybe haven't seen before, we're going to add it to the dictionary so that if it shows up again, we have a short way of describing it. So as we kind of see the same sequences of characters again and again, we'll have an easy way to compress them because we can effectively say, oh, this is that same thing you saw before. So I've got a picture here that shows what our dictionary looks like. The first 256 entries are going to be fixed, or they're going to be set before we even start doing compression. Every one of those is going to be is going to correspond to an individual byte value that could show up in the file. So if you think of the dictionary as having a bunch of words in it, then the first 256 words are just single byte words. We're going to have the first one will just be the byte 0. Same thing we use as a null terminator in a string. So if byte 0 shows up in the file, we've got a way of saying that by saying, oh, that's word number 0 in the file. If byte 1, or if a byte with a value of 1 shows up, we've got a word for that. We'll say, oh, that was word 1, all the way up to the, these are the smallest possible byte values we could get, all the way up to the largest one, written in hexadecimal. FF is the biggest value that could be in a byte, and that's word number 255. So these first 256 words are already taken in the dictionary. But if we're using more than 8 bits per code, and remember our program by default uses 10 bits per code, then our dictionary can have more than just those 256 initial entries. Like it says in the write-up, if you've got B bits per code, then our dictionary can have 2 to the B entries in it, where B is the number of bits. So if it was by default 10, then our dictionary would have 1,024 entries. The first 256, so the first quarter of those, are reserved for these 1 byte words. But then all the rest we're going to use for words that we encounter as we're compressing the input file. And they'll give us a quick way of writing out sequences or handling sequences that have already occurred in the file. Let me say an example for this. So the first time you see AB, you might have to write that out as the code for A. Well, that's going to be one of these first 256 codes, followed by the code for B. But you're going to go ahead and add that to the dictionary so that if it shows up again, you have a single code that you can write out to say, oh, it's that same AB you saw earlier. Here's just another copy of it. So that's why to get compression, we're generally going to want space in our dictionary for adding new words. And the bigger we make that value be, the more room we've got to grow our dictionary. So if B is 10, we've got 1,024 entries in our dictionary. So after the first 256, that's more than 700 spaces to add new words. If we made B bigger, and that's a command line option in the program, if we made it 11 bits, then we'd have a lot more entries that we could fill in as our program runs. Now, we'll talk through an example and we'll see how stuff gets added to the dictionary as we're compressing a short file. But the dictionary, as the compressor sees new sequences of bytes, new words in the input, it'll add them to the dictionary, and then we have a short way of describing that sequence if it shows up again later. When we actually write out the compressed file, we're going to write it out as not a byte at a time, but as codes, where the code length is determined by the number of bits given on the command line. By default, that's 10, so that's what this picture shows. So the first code we write out is going to be a 10-bit number. That's going to, well, in a file where every byte is 8 bits, that's going to use up all 8 bits out of the first byte, and we're going to have to use the next 2 bits in the next byte. And then if we wrote out another 10-bit code after that, that would use the remaining 6 bits in that byte, plus the next 4 bits in the byte after that. So since we're writing out codes that consist of more than 8 bits, at least we're going to be able to do that, our codes will the bits in a code will be spread across potentially more than 1 byte. And this just shows how that would work if you had a bunch of 10-bit codes. In this case, 4 10-bit codes, you'd need 5 bytes to write those out. So this is the same example that's shown in the write-up. We're going to show what the compressor should do as it's compressing this, and I'll sort of talk you through this as we go. Up here, this is, if you look at, I think it's input number 5. It's the same one that's described in the assignment. It's just this sequence of characters. It's a bunch of letters, A through C, with a new line at the end. So it's a text file. It's got a new line at the end of that first line. This shows what the input looks like. Down here, we're going to show the codes for the compressed output. And over here on the right, we're going to show what happens to the dictionary as we're compressing this file. And this picture on the right shows what it looks like initially. We're pretending we're using 10-bit codes here, just like that test case given out with the assignment. So the first 256 entries are just single byte words. And then the rest of them are kind of room to grow the dictionary based on what the compressor sees as it's reading in the input. So the compressor, it says this in the write-up. It says it's always going to take the next sequence of bytes from the input, and it's going to look for the longest dictionary word that matches the next sequence of bytes from the input. Initially, all we've got are these 1-byte words. So initially, the longest word we're going to be able to find is the word that matches this A. The ASCII code for A is a 97. So that it's not shown in the picture, but that's going to be line 97 in the dictionary. Initially, we just have those 1-byte words. So the longest word we can match is, like I said, just this A. So we'll write out the code for A. A is on line 97 of the dictionary. So we write out 97 to the compressed output. We write out the code for that as a 10-bit code. Here I'm showing it in decimal, but when you write it out, you're really going to be writing it out as a sequence of bits. And the compression algorithm says, well, whenever you write out the code for a word, you're going to add that word plus the next character to the dictionary, because here A was the longest word that we had in the dictionary right now, but it was followed by a B. If we go ahead and put AB in the dictionary, then if we happen to see that sequence again, we'll have a short code for it. So again, and it says this in the compression algorithm, whenever you write out the code for a word, you're always going to go get the next character from the input. We called that X in the write-up, and you'll take that word plus that one next character. We called it W concatenated with X, and you'll add that to the dictionary, and that's what we're seeing here. A was the word we just wrote out, or at least we wrote a code for it, plus the next character B. That got added to our dictionary. Again, the plan is, if we happen to see an AB again, we'll have a short code for it. In the output file, like I said, we're going to write out that code 97, but we're going to write it out as a bunch of bits. So that's 97. This is what it looks like in binary. If I had to read it real fast, I would say hit 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. So that's a 10-bit code. That's just the number 97 written out in binary. We needed the whole first byte for that and 2 bits in the next byte. And it says this in the write-up, we're always going to start by using the high order bits. And then we'll, you can see we've got these 6 low order bits left over in that next byte. We'll use those when we write out the next code. So the next code will pick up right from here. It's high order, the next code, its high order bit will go here, and then its next bit will go here, and it'll fill up these 6 bits like we saw before, plus 4 bits in the next byte. There are a couple of questions that you might be thinking here, and that is, how do you write out binary codes to a file? And if you got a number, like we said, we got a number 97, how do you get that number in binary so that you can write it out to a file? And for both of these, I've got hopefully a good answer. For writing out codes to a file, our plan for making that easy is the buffer component. The buffer lets you hold a bunch of bytes in memory and then write them out later. And that's our plan for what we're going to do with the code. You'll really be writing those into the bytes of a buffer. And remember, buffer has a couple of functions to make it easy to look at individual bits and change individual bits. So once you've got the code for a word that you need to write out, like backing up like this, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, you can just have a little loop that writes out those bits into your buffer. And since buffer has, I think it's a function called set bit, you could just loop through and write out those 10 bits one after another into successive bits of your buffer. If you wrote that function correctly, and it's not that hard to write that function, writing out codes or the bits of the next code should be pretty easy. And then, like I said, the plan is you'll write those out into the buffer. And then once you've written out the entire contents of the compressed file, you'll make one more function call to ask the buffer just to save all of that to a file. So the reason we're making that buffer component is to make stuff like this a whole lot easier. How do you get a number in binary? Well, that's going to be easy because if you've got something like a code 97 stored as an int, then internally it's already in binary. Int values are stored in binary in computer memory. All you have to do is be able to look at the individual bits for how that code is stored. And we learned the bitwise operators to do that kind of thing. You can do something like build a movable mask to look at whatever bit you want. So you could use this to write a loop that looped over all the bits of a code. You don't have to convert that code or anything. Like I said, it's already in binary if you just look at it a bit at a time. And you could loop over the bits in a code and write them out to a buffer 1 bit at a time. So going back to our compression task, here's where we left off. We had written out the code for A. Like we just said, we'll write that into a buffer in binary. And the compressor said its policy is I'll go ahead and add that word plus the next character to the dictionary in case I see it later. So I'll try to go a little bit faster here because we've got several characters to get through. So now we've taken care of the A, so now we're at the start of that B in the input. B is in our dictionary. It's in one of these first initial words, but BA is not. So the compressor always tries to write out the code for the longest word that's in the dictionary. So B is in the dictionary. Again, it's one of those first 256 words, but BA is not. So we'll have to write out the code for B. That's a 98. But let's go ahead and add B plus the next character, BA, to the dictionary in case we see it later. So now the compressed output has 2 codes in it. They're going to look like this if we looked at them in binary. We've used the whole first byte, the whole second byte, and 4 bits out of the third byte. We've got 4 more bits that we'll use for the next code. So as we write out codes, internally, you're going to be growing your buffer. and writing out bits of each code. Again, adding on bytes as you need to have room for bits that you need to write out. So backing up a slide, we just wrote out the code for the B. So now we're at this A in the input. A is still in the dictionary, but AC is not. So bumping ahead 2 slides. So we'll write out the code for A and we'll add AC to the dictionary. So there it is on line 258. Now continuing from the C, C is in the dictionary, but CA isn't. I'm just looking at the next, after we write out the code for A, we're right here in the input. So the next character we have to write out, or the next byte we have to write out, is a code for C. C is in the dictionary, but CA is not. So we write out the code for C. That's a 99. We add CA to the dictionary in case we see it later. Next, we got to write out the code for, or we got to deal with input starting at A, but AB is already in the dictionary. We added that a little while ago, but ABC is not. So we can write out a code for AB, and this is where we start getting compression. At least we start getting some benefit from compression, because now we can write out just one code. AB is on line 256 of our dictionary. So you write out the code 256 in binary. That covers the sequence, the word AB, those 2 bytes. And even here, we'll add ABC to our dictionary, because AB was the longest word we had a code for, but maybe we're going to see ABC again. So we go ahead and add that. Continuing, next, CA is the longest word that's already in our dictionary. So we write out the code 259 for CA, and we add that word plus the next character, CAC, to our dictionary. Continuing, C is in our dictionary, but CB isn't. So we write out the code for C and add CB to our dictionary. That's this red line here. Continuing, BA is already in our dictionary. So we write out the code for that. Here, one code is going to give us 2 characters. So we're getting compression. And we go ahead and add BAB, the word we just wrote a code for, plus the next character. We add that to our dictionary in case we see it later. Continuing from this, BC is not in our dictionary. So we write out a code for B and add BC to our dictionary. Continuing from the C, we've already got a code for CAC. That's on line 261. So we write out that code, and then we add the even longer word CACB to our dictionary. So you can see every time we have a code, or we have a sequence of characters where it would have been nice to have a code for an even longer word, we go ahead and add that word to our dictionary. So now we're all the way up to this B. We've got a code for B, but we don't have a code for B new line. So we write out the code for B and we add B new line to our dictionary. Here, I wrote it as a \n, like you might think of it in a string. In the dictionary, I wrote it out in hexadecimal, and 0A is a new line in hexadecimal. And that's to match the way we report the dictionary. Remember, there's an option -D that gets your program to just print out the dictionary when it's done. So I tried to write this down in a way that would match that report. So we've added B followed by new line to the dictionary. Now we just have this one last byte to write out. It's in, new line is a 10 in ASCII. Same thing as 0A if we wrote it out in hexadecimal. So we write out the code for that. Here we can't, we're at the end of the input, so we can't add a new word to our dictionary because there's no next character. So when you're at the last word, when you're writing out the code for the last word that you can write out, you can't add another word to the dictionary then because there's no next character. I think the pseudocode in the write-up handles that kind of thing. I guess I would also say once the dictionary is full, you'll still be writing out codes, but you won't be able to add any new stuff to the dictionary. So if you think of these green words as stuff that the compressor learned as it was writing out the compressed file. Once you fill up the dictionary, you can't learn any new words. All right, so this is what the compressed output would look like. But of course, here we just wrote it down as a bunch of decimal codes with commas in between them. In the actual output, it would just be, 10-bit code followed by another 10-bit code followed by another 10-bit code in the output, or whatever bit width you pick for the compression. For decompression, so same as the write-up, I wanted to talk through how the decompressor works. It's a little simpler than the compressor because it kind of just has to do what it's told in the compressed input file. We're going to rebuild, the decompressor is going to be doing kind of two jobs. It's going to rebuild the original file based on the sequence of codes it sees in the compressed file. And it's going to build the dictionary as it does this. It doesn't have to be told what the dictionary is. It'll kind of simulate what the compressor was doing when it wrote out the compressed file, and it'll automatically construct the same dictionary just by looking at the sequence of codes. So here we're going to do the same thing backward. We'll pretend we're the decompressor. When we look at the input file, it's just a sequence of codes, for us, 10-bit codes by default. We're going to build the uncompressed output. And as we do that, we're going to fill in the dictionary, because you can see some of these codes are for dictionary words that we better figure out before we get to these codes. Otherwise, we're not going to know what to do with them. And we should be able to do that. So let's give it a try. So if you're the decompressor, your first code is 97, and you start out with the same 256 dictionary entries for free. So 97 is already in your dictionary. Oops. Here, I'm just reminding us kind of what I just said. As you're reading the input, you're reading these codes, but you'll be reading them as sequences of bits. I guess I would say here also the buffer is going to make this kind of easy, because my plan is you're going to take the entire compressed input file and read it into memory all at once. And then to get a code, you'll just use I think it's the get bit function to look at 10 bits at a time, turn those into an integer, and then you just have to look up that line of the dictionary. So for this first code 97, line 97 of the dictionary says that's an A, that's a 1-byte word for an A. So we'll write that code to the compressed output. At this point, the compressor would have added a word to its dictionary, but we can't do that until we know what the next character is. Because when it wrote out this 97 for the A, it would have added A plus whatever the next character is to the dictionary. We don't know what the next character is, but we will as soon as we decode the next word. So continuing, the next code is a 98. That's in the initial part of our dictionary. That's the code for B. So now we know the next letter is B, and now we can go ahead and add the first word the compressor would have added to its dictionary. It would have put its first word A, followed by the next letter B into the dictionary. So we go ahead and put AB in our dictionary, so that if a 256 shows up in the sequence of codes, we know that's the code for an AB. At least that's what the compressor would have used as a code, as the word as word number 256. All right, the next code's a 97. That's the code for another A. When the compressor wrote out the code for this B, it would have added that word, just a B, followed by an A as the next word in its dictionary. So we do the same thing. You could go back and compare. We're growing our dictionary exactly like the compressor would have. Continuing, the next code's a 99. That's a code for a C. We know the compressor, when it wrote out the code for the A, it would have added AC to its dictionary. So we do that. Continuing, our next code is 256. You can see that's the code we added earlier. That means the next input must have been an AB. And we know when the compressor wrote out the code for C, it would have added C plus just the next letter, because it's always adding a new word to the dictionary. That's the previous word plus just the next character. Well, here the previous word was a C plus the next character an A. So it would have added CA to its dictionary. The next code is 259. That's CA. So we know those are the next 2 bytes. And the previous word AB plus this next character C, the compressor would have added that to its dictionary. So we do the same thing. The next code is 99. That's a code for a C. The compressor would have added CAC to its dictionary. So we do that. The next code is 257. That's BA looking at the dictionary. So our next 2 characters must be BA. And the compressor would have added CB to its dictionary. The previous word, C, plus just the next 1 character, this B. So we add that to our dictionary. The next 98 is a code for B. So we put B in our uncompressed input. That's the next byte in our output, or in what's going to be our output. And then we add A, or actually BAB. The previous word was BA, plus this 1 next character B. That's the next thing that goes in our dictionary. The next code, 261, gives us 3 characters. We add that to what's going to be our compressed output, and we go ahead and put the previous word, just this B, plus the next character C to our dictionary. That should be what the compressor did. That should be what it added as its next dictionary word. We're almost done. The next code is 98. That's a B. Now we know the compressor would have put CAC, the previous word, plus that B in its dictionary. So we do that in case it shows up later. Our last code is a 10. That's the code for a new line. We go ahead and add this to the dictionary. B was the previous word, followed by this next character, the new line. And again, I wrote that as B followed by 0A. That's the ASCII code for new line in hexadecimal. And now we're done. We've recovered the entire compressed input. We can tell that because we got to our last code. If you're reading this from a file, there wouldn't be enough bits left in the file to get another code, so you know you're done. We've got, if you go back and check, this should exactly match the input that the compressor started with, and you could even compare this dictionary. We built a dictionary as we were doing this that should be exactly the same as what the compressor built. That works through those 2 examples, and hopefully with a little bit of the explanation, this makes a little sense. I'll try to pay attention, and if there's something else I can record like this to help explain it, I'll try and get that posted. Good luck on the project. I'll see you in class next week.